Okay, so since the TA hasn't arrived yet, as far as I see, I think I'm just gonna start now. Hope y'all are ready. So today for Math Divulge, we're gonna talk about equations, but drawn. I guess because visualization for equations is a pretty good way to visualization for anything and not even just visualization in the sense of like seeing something, but just like being able to know the depth of it. Like say even if you're blind, um, you have your own sense of like perception, and that sort of perception that's attached to your senses, like your senses can help you like understand certain things better. So uh yeah, like drawing, visualization, um it's usually a pretty good way to better understand a topic like equations. So um we're just gonna start with something that uh okay, I need to move this down, drag this down. So all right, we're just gonna start with something that y'all probably know how to do. So say we have the equation 4x equals 12, right? So how do we solve this? Well, we just do 4x equals 12, so divide by 4, we get x equals 3. Now, how do we visualize this? So x is a number, and the way we visualize numbers is on a number line. So here we have a number line, a 0 in the middle. That's a bad 0. A 0, and then 1, 2, 3, 4, 5, and so on. And then -1, -2, -3, -4, and -5, and so on. And then, so x is 3 would be right here. So if we have one equation in like this, not really like fancy in any way, well, we just get one value for x, and it's somewhere on the number line. Now, if we have something like 4x plus 8 equals 12, oh, that just becomes 4x equals 4, and then x okay, yeah, that just becomes x equals 1, and so that would be this point. So if we have this other constant right here, we can move it to the other side, or sometimes we want to move the 12 to the other side, so 4x minus 4 equals 0. Either way works. We just get, it's a simple equation, and we just get a single value for x and put it on the number line. And the number line is how we visualize it. Now, what if instead of just x, we had y? So let's see how to do this. So instead of just x, we had y, and we had an equation like 4x plus 3y equals 12. Well, what values satisfy this? what do x and y look like? So one thing we can do is just try to come up with a few easier values. Um, so say, what if x was 0? If x is 0, then 4x would be 0, and then 3y. So if x is 0, then 3y equals 12, y equals 4. Right. Now what if y was 0? So if y was 0, then 4x equals 12, and then x equals 3. So the points 0, 4, the pair for xy, 0, 4, x equals 0, y equals 4 satisfies this. And then the pair 3, 0 also satisfies this. Okay. So can anyone guess what all the values that satisfy this is going to look like? And probably some of you have learned this before, but one way to, but you're going to end up getting a line. Okay, so for this thing here in one variable, this linear equation in one variable, you get a point. And now with two variables, you get a line. So, well, a line on what? So one way to see this is, okay, so x and y are, xy is a pair of numbers. So we can, so instead of just one number line, one straight line for x, we extend that. So here is the x-axis, and then we extend it upwards and downwards in the y direction. So we get, so yeah, we see, if we mark these off as 1, 2, 3, 4, 5, and so on. 1, 2, 3, and so on. 1, 2, 3, 4, 5, 6, and so on. Then we see that 0, 4 is a point. So when x is 0 and y is 1, 2, 3, 4, you get a point. That satisfies this equation. When x is 3 and y is 0, that also satisfies it. So 1, 2, 3. So these 2 points satisfy it. And then if we write one of them in terms of the other, then we can do, for example, say, and we can we can try to find more values. For example, if we say x is 6, if x is 6, then 4x is 24, and then so subtracting 24, you get 3y equals negative 12. And then so 3y equals negative 12 means y is negative 4. So 6, negative 4 also satisfies this. And it would be somewhere like here. So we see that all 3 points are, they're not some random 3 points. And we can systematically go about coming up with new points that satisfy 4x plus 3y equals 12 by, say, writing y in terms of x. So we can start by moving x to the other side. So 3y equals negative 4x plus 12. And then y equals negative 4 over 3 times x plus 12. Now we see that for any value of x, like say x is 3, x is 6, x is 5 or 4 or anything, we can put that value into this equation right here, and then we can get a corresponding value of y. And it turns out that corresponding value of y is going to draw a line. Create a line like that. So all the points on this line satisfy 4x plus 3y equals 12. Right. And if we look at the original equation, 4x equals 12, in terms of just x, it's a point, right? 4x equals 12 gives the point x equals 3. But if we graph it here on the 2D plane, x equals 3 is actually another line. So x equals 3 and y equals 0 is here. X equals 3, y equals 1 is here. And then x equals 3, y equals 2 is here. So it doesn't matter what y is. You get a line for x equals 3. Okay, so we've done one variable, we've done two variables. You might have seen this in your other classes before. But what about 3 variables? So let's see. Okay, clear our drawings. What about 3 variables? Let's say take the equation 4x plus 3y plus 2z equals 12. Well, like the previous ones, we can start out by guessing a few values. So if y and z are both 0, then we get 4x equals 12. If y and z are 0, then these two terms cancel away and we get 4x equals 12. So x equals 3. So 3, 0, 0 is a point. What's another point? Well, if we eliminate x and z by 4x and 2z by setting x equals 0 and z equals 0, then we get 3y equals 12, so y equals 4. And finally, if we set x and y equal to 0, so x, y, then we get 2z equals 12, so z equals 6. Well, how do we visualize this though? So we started out with just a one variable equation, 4x equals 12. And for the one variable equation, we just drew it on a horizontal line. And then we had 4x plus 3y equals 12. And for an equation in 2 variables, we drew it on a plane. Now we have 3 variables, 4x plus 3y plus 2z. So x, y, and z. So start with a line. You have a plane. Now, what's another dimension? That dimension. We have depth. So it's a little hard to draw on a whiteboard because a whiteboard is basically flat and 2D. But what we can do is go through the origin and just imagine that this has depth. Right, so x, this is the x-axis, this is the y-axis representing y values, and this is the z-axis. So, okay, so we can now plot these points. 3, 0, 0. So 1, 2, 3. 3, 0, and then 0 in the y direction, and then 0 in the z direction. So it's just this point. 0, 4, 0. So 1, 2, 3, 4. That would be this point. 0 in the 4 in the y direction. And then finally 0, 0, 6. So 1, 2, 3, 4, 5, 6. 6 in the z direction and 0 in the x and y direction. So you have 3 points that are part of all the many values of x, y, and z that satisfy 4x plus 3y plus 2z equals 12. So what do we think this, all the values are that satisfy this are going to turn out to look like? Well, you might guess that it's a plane. And so, well, what can we do? We can, like last time we wrote, in order to generate more points, we wrote y in terms of x. And now we can write z, put z on one side and put x and y on the other. So 2z equals negative 4x minus 3y minus plus 12. And so z equals negative 2x minus 3 over 2y plus 6. Okay, so then for example, if we say x is 0, for x equals 0, we have all z and y satisfying z equals negative 3 over 2y plus 6. And that, so if x is 0, then z equals negative 3 over 2y plus 6. And that looks just like what we got when we put y on one side and x on the other for 4x plus 3y equals 12. So in two variables. This is just a linear equation in two variables. And so what's a linear equation in two variables? That's just a line. So it turns out we get this line right here. And then say if x equals 1, then we have negative 2 times 1 minus 3 over 2y plus 6. So this negative 2 combines with the negative, with the plus 4, and we get that if x is 1, then this equation becomes z equals negative 3 over 2y plus 4. So it's for x equals 1, we're going to have a line that's a little bit lower, and then a little bit lower, and then a little bit, and then it goes through this point. So all in all, we have all these lines, and they rise as x goes to the left, and they lower as x goes to the right. And so what we have here is a plane. So it's kind of hard to draw a plane here, but it's going to be a plane. Like the x and y axes together, they make a plane. And then the plane that satisfies x 4x plus 3y plus 2z equals 12 is a different plane. Okay. So now what we've been working with so far are all something times x plus something times y plus something times z. And so we might think, oh, it's a little boring. Like x and y and z, they're all like, there's no x squared or y squared. And so now we'll start to, now we'll look at something with x squared and y squared. Yeah, so a simple example we can start off with is x squared plus y squared equals 25. So the thing is, without a TA, I can't look at the chat. I can't see the chat, so okay. Oh yeah, it seems like many of you are getting the answers, which is yeah, many of you are getting the answers, which is really good. Okay, so yeah, now we're on to the equation x squared plus y squared equals 25. Now, what points satisfy this? And some of you are already getting what the answer, what it's going to look like. Not, I'm not going to reveal it right now to some of you who haven't uh, seen this before. But basically, well, we can test it in the same way, right? If x is zero, then we have y squared equals 25. So y can be uh, plus 5, or it can be minus 5. So okay, sorry. So what happened was um, my Zoom suddenly crashed. I don't know. It happened last time as well. So it was either a problem with my computer overheating or a problem with Zoom. But hopefully we can get it back up. Share screen, whiteboard. But so I guess we can go back to okay, so what we had earlier was x squared plus y squared equals 25. And what we said was, okay, so if x is 0, that's one way we can test for values that might satisfy this. If x is 0, then y squared equals 25. So y is plus or minus 5. So we have 0, 5, 0, negative 5. And if y was 0, then we have the same thing but for x. So x squared equals 25. So x is 5 or minus 5. And if we graph this, if we plot this on the x and y axes, we have 0, 5. So, or I'll do the tick mark thing. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have 5, 0, 5, 0. That's this pair xy right here. Negative 5, 0. This one right here. 0, 5. This one right here. And 0, negative 5 right here. So we have 4 points that are here, 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 and here. So what other points do we have? What do we predict? And some of you said what the shape is already, and y'all got it right. But what is this for everyone else? What does this equation remind you of? 25 is a square. It's 5 squared. So it's x squared plus y squared equals 5 squared. So something squared plus something squared equals something squared, which is the Pythagorean theorem. The Pythagorean theorem is basically, it applies to right triangles, and we have, and it basically says if you have a right triangle with sides x, y, and say z, then x squared plus y squared equals z squared. And in this case, z is 5. So x squared plus y squared equals 5 squared. And the converse is true. So if you have x squared plus y squared equals 5 squared, then the sides form a right triangle. So that means, so what values for x and y do we recall from the Pythagorean theorem? One such pair x and y is 3 and 4. So 3, 4, 5. That forms a right triangle. So we know that 3, 4 works. But it doesn't matter if 3 is x or 3 is y and the other way around. If it's 3, 4 or 4, 3. So 4, 3 also works. And we can also, and although lengths are positive, and negative lengths would require a different treatment, but here on the x-axis and y-axis, you can have positive or negative. So 3, negative 4 also works. 4, negative 3 also works. Negative 3, 4, negative 4, 3, and so on. So we have here 4, 3, 3, 4, negative 4, 3, negative 3, 4, 4, negative 3, 3, negative 4, 3, negative 4, 4, negative 3. And so we have this point, this point, this point, this point, this point, this point, and all these points. So we can probably guess what it's going to turn out to be, right? It's going to be a circle. And all these points here satisfy the fact that their distance to the origin, to 0, 0. So x, y being 0, 0 is called the origin. So their distance to 0, 0 is always 5. And we can see that because if we draw this right triangle that looks like this, and x, and label it x and y, we have x squared plus y squared equals 5 squared. So every point here satisfies x squared plus 5 squared, y squared equals 5. Every point inside the circle satisfies x squared plus y squared is less than 5. Every point outside satisfies x squared plus y squared is greater than 5 squared. Okay. So the thing is, how do we go about doing this systematically? So for the last one, 4x plus 3y equals 12, we wrote y in terms of x. Here, well, what's y in terms of x? Let's put y on one side and x on the other. So y squared equals 5 squared minus x squared. So y equals the square root of 5 squared minus x squared. The thing here is that it can be plus or minus, right? So plus or minus the square root of 5 squared minus x squared. So there are two values of y that satisfy this. For example, for x, if we have x is 0, then it's plus or then y squared equals 5 squared. So y can be 5, or y can be negative 5. So for x is 0, y can be 5, or it can be -5. So there's two values. This isn't exactly a function. Well, so is it a function of anything? Is this a function of anything? When when we draw a function, usually say you draw a function like this, what you do is you do it, say, from left to right or right to left, something like that, right? So here, when we move from left to right, we see that for every x, there's two values of y. From here to here, there's two values of y. And functions are so that for every value of x, there's exactly one value of y. So it's not exactly a function in terms of x. Well, how do we draw it so that we go 1 point at a time? Well, just the way we draw it, right? Like this. And so the thing is, if we start here and then go around, we're going through 1 point at a time. And that point is in terms of time. So in terms of some time t. So say at t equals 0, can I erase this stuff? Say at t equals 0, we start at 0, 0. And then at t equals 1, we go one length along the way. So yeah, that's going to be some value of x and y such that x squared plus y squared equals 5 squared. And if we look at the right triangle here, we see that it satisfies, it's a part of this right triangle, right? And one of the things about right triangles is that the legs of the right triangle actually correspond to trigonometric values. So if some of you are new to this concept of trigonometry, basically it's if you have a right triangle with hypotenuse 1 and then some angle t here, then this side closest to t is going to have the length cosine t. And this side opposite of t is going to have the length sine t. So here in this bigger right triangle, this is not to scale. 1 to 5 is way more drastic than this comparison. But here, if we scale this right triangle up by 5, then we have, instead of x, we have 5 times cosine of t. And then y would be 5 times sine of t. So in another way, cosine is the adjacent over the hypotenuse, and sine is the opposite over the hypotenuse. Right, so now that we have 5 cosine t and 5 sine t, we can write this as a pair. 5 cosine, and when t is 1, then it's just cosine of 1. And then and then the y would be 5 sine of 1. And just in general, we have x and y. In general, we have x and y being 5 cosine of t, 5 sine of t, as we go all the way around this circle. Okay. So now that we know how to draw this circle with radius 5, Well, how do we draw something that's twice as big? So this if this circle has radius 5, then what would be the radius of the circle that's twice as big? It would be something like this, right? It would have radius 5 times 2, which is 10. So how do we get um, the values that satisfy that x and y so that they lie on this circle? Well, one thing we can see is x is multiplied by 2, y is multiplied by 2. So if we look at this parametric equation, and this is called a parametric equation because it's written in terms of a parameter, t. A parameter is like this extra variable that makes identifying certain things easier. So t is the parametric variable here. And so if x and y are multiplied by 2, we get, instead of 5 times cosine t, we get 10 times cosine t. Instead of 5 times sine t, we get 10 times sine t. So that's one way to represent this. What's another way? Another way is if we look at the radius being twice of this smaller circle, you have the radius, instead of 5, it's 10. And so what's the relation between x and y that gives this radius being 10? Well, like how we figured out this is a circle, we can drop down this height right here and form a right triangle. And we have this side length being x, this side length being y. So x squared, so by the Pythagorean theorem, we have x squared plus y squared equals 10 squared. Right, so x squared plus y squared equals 10 squared is the same as the parametric equation, 10 times cosine t, 10 times sine t. Right. Now, how do we shift this circle 10 to the right? That's another transformation we can do. So first we enlarge this smaller circle by 10 and came up with this bigger circle with equation x squared plus y squared equals 10 squared. Now I'm going to erase this original circle. Right, and we're going to try to move this big circle 10 to the right. Let me try to see if there is any questions so far. Yeah, a lot of you are getting it. Really good. Yeah, so now we want to move this big circle 10 to the right. And what would that look like first? Before we come up with an equation, what would that look like? That would look something like this. Okay, so this point right here, move 10 to the right, goes to this point right here. And it's supposed to be the origin, but the drawing on the whiteboard is a little different. So this point right here goes 10 to the right. This point right here goes 10 to the right. This point right here goes 10 to the right. And this point right here goes 10 to the right. The center also moves 10 to the right. So, so what equation describes this new circle? originally we had the equation x squared plus y squared equals 10 squared. So some function of x, and yeah, this is basically a function basically saying you do something to x, and then plus some function of y gives you something, right? So I'm just going to use very random variables to say you do something to x and you do something to y, and you get something. And now now that we want to move it 10 to the right, we want values. We want to say that if x and y are on the original circle, then we want x plus 10. So xy move 10 to the right. We want x plus 10 and y to be on the circle as well. So how do we do this? So if we know that f of x plus f of y equals c is satisfied by x and y, then how do we get x plus 10 and y to satisfy some equation? Well, the thing is, we can write x in terms of x plus 10. So now we want to center everything around x plus 10. We want to write everything in terms of x plus 10 instead of x. So instead of f of x, we write f of x plus 10. But the thing is, we know that f of x satisfies this equation, and we don't know anything about f of x plus 10 yet. So we're going to turn this new equation into something that looks like the old equation. So x is just x plus 10 minus 10. And we know f of x satisfies this. So we still know that this is true because x plus 10 minus 10 is just x. So these two are basically the same equations. But now notice that we wrote everything in terms of x plus 10, right? So if xy satisfies this equation, then x plus 10y satisfies this equation. And what it would look like if we wrote it as an equation would be, so if x plus 10 was the new x, right? So if x plus 10 was the new x, if we had an x over here, then we would have x minus 10 squared Wait, apparently my computer crashed again. Hopefully it'll yeah, hopefully it'll work this time. Okay. So what did we have before? We had the equation x squared plus y squared equals 10 squared, which is 100. and we drew it here. And then we shifted it 10 to the right. So we had this circle here. Okay. And so what we did was we saw that in order to shift to turn xy, an xy that satisfies the old equation to an xy that satisfies that is on the new circle, so x plus 10y, we had to do x minus 10 squared plus y squared equals 10 squared. So why is this? If we look here, if we go the other way, instead of using this circle to find the equation, we can look here to see what values of x and y satisfy this equation. What values of x and y satisfy this equation? So we can do the old thing. If y is 0, then x minus 10 squared equals 10. If y is 0, then x minus 10 squared equals 10 squared. So x minus 10 equals plus or minus 10. If it's minus 10, then minus 10 plus 10 means x is 0. If it's plus 10, then x minus 10 is 10 means x equals 20. So x equals 20. So if y is 0, then x can be 0 or 20. So these points do, in fact, line up on the new circle. In fact, for any value of x and y that are on this new circle, we have that because the center of this new circle is 10, 0. So if we draw this right triangle right here, we get that this, because now instead of this leg of the right triangle being x, we have this length from the origin to this point right here being x. So not from the center to this point, but from here to here being x. So then in order to plug this into the Pythagorean theorem, you need to subtract this length right here, which is 10. So this leg right here is x minus 10. And this right here is still y. And then this right here is 10. So by the Pythagorean theorem, we have x minus 10 squared plus y squared equals 10 squared. Now, as a parametric equation, this is a lot easier. Originally, for the triangle to the left, or for the circle to the left, we had 10 times cosine t, 10 sine t as x and y. For this circle right here to the right, well, to move it to the right, all we have to do is shift x. So x, instead of 10 cosine t, we have 10 cos t plus 10. And then 10 sine t. Right. So we can easily transform a circle in any way. We can enlarge it 2 times, 3 times, or shrink it by some factor. We can move it around, and we can do all kinds of stuff to it. And just in general, we have the form x squared plus y squared equals the radius squared for this equation right here. And for the parametric one, we have just the radius times cosine t, and then the radius times sine t. right? And if we want to shift it around, then we, instead of just x squared, we can have x minus the center. Say we call uh, the center here, we call it, say, x0, y0. Then we have x minus x0 squared plus y minus y0 squared equals the radius squared. And recall that this just basically follows from the Pythagorean theorem. And the corresponding one with the parametric equation is, again, you just shift x and y by x0, y0. So a cosine t plus x0, and then a sine t plus y0. Okay? So now now that we dealt with x squared plus y squared equals 100, right, so now that we dealt with x squared plus y squared equals 100, what if we change this y to be 4y squared equals 100? Now, what shape would that be? What is this equation? Okay, so yeah, what shape would that be? Some of you might be able to, let me open up the participants list. Some of you might be able to guess this shape. It's an ellipse. Now, what is an ellipse if you didn't know? So what equation does this remind you of? This is just like this equation, but instead of y squared, it's 4y squared. And we can even write 4y squared as a square itself. X squared plus 2y squared equals 10 squared. So originally we had a circle like this. Where it's centered at the origin and it has radius 10. And now we have that instead of x and y, if the point here, x, y, solve the original equation, x squared plus y squared equals 100, then the point x, then how do we get a corresponding point that satisfies this new equation? So if plugging in y to this works, then 2y, for xy to work here, we would have to plug in 1/2 y. So if xy satisfies the old equation, then or if x1, y1 satisfies the old equation, x squared plus y squared equals 100, then x1 squared plus 2 times 1/2 of y1 squared. If we do this, then the 2 times 1/2 would cancel, and x1 squared plus y1 squared would equal 10 squared. So now that would mean we have to plug in x1, y1 divided by 2. So 1/2 of y1. And then similarly for here, we would have to half it. For here, we would have to half it, and so on. And so what we would end up with is this shape. So it's, yeah, something like that, right? And this is what is called an ellipse. And how do we parameterize it? Well, since we're having all the y's, right? Originally we had for x squared plus y squared equals 100, we had 10 cosine t Okay, so originally had 10 cosine t, 10 sine t. Now that we're halving y, we have 10 cosine t, 5 sine t. So these x and y satisfy the ellipse. So all in all, we're scaling everything. Right, so the general form would be, instead of 10, we can write a. So something times x, something times cosine t, and then something times sine t. And then just as we scaled, we made y squared into 4y squared, we can actually make x squared into something, say, 25x squared. 25x squared plus 4y squared equals 100. Now, what do you think that would be? It would still be an ellipse, but what would change? So here, instead of 1x squared, we have 25x squared, and 25 is 5 squared. So we can write this as 5x squared plus 2y altogether squared equals 10 squared. So that would mean the same for some x and y that satisfy this old equation. We would have to plug in 1/5 of that x and 1/2 of that y to satisfy this new equation. So it would be an even shorter ellipse, or more smushed together ellipse, something like that. Right? If we want to look at it without looking at the original circle, this is an ellipse, and then this is another ellipse. Okay, so those are the ellipses with the original circles. And so basically, we have some constant times x squared plus some constant times y squared equals something. And in order to make the number of constants we use in writing the general form of an ellipse as small as possible, so we don't want to say, like, we have something times x squared plus something times y squared plus something times, or equals something. So that's 3 constants. We can define it with with much less, or not exactly much less, with 1 less, right? We can, instead of writing the last constant, we can divide everything by it. So divide 25 by 100, divide 4 by 100, divide 100 by 100, and we get something times x squared plus something times y squared equals 1. So what would that be? 25 divided by 100, that would be 1/4. So x squared over 4, and then 4 divided by 100, that would be y squared. That would leave us with y squared divided by 25, and then 100 divided by 100, that would leave us with 1. So whatever is on the right-hand side, we can always divide it by itself. And so we have something of this form, which in general is, if we write it on the left, if we write it on the left, in general, this is x squared divided by a squared plus y squared divided by b squared equals 1. Right? And this equation right here corresponds with this parametric equation here. They give the same ellipse. And what are ellipses used for? Ellipses, well, Yeah, like think for a sec. Where do you see ellipses? You see circles everywhere for sure. Where do you see ellipses? So it turns out if we look at the orbits of the planets, they're in an ellipse. In the past, some weird European people or people in ancient Europe would say, "Oh, like they look like circles with circles in them," and it would just be these very complicated ways of describing the orbits. And they would always try to refine it because it would never be completely accurate. And eventually some math guy came in and said, "Wait, no, these are just ellipses." And here are the physics you can use to show that they're ellipses. So if we look, um, let's see, on my other screen here. So this is what an ellipse would look like. This right here. This is an ellipse with eccentricity 0. So eccentricity is this other property of ellipses. It's something you can write in terms of the other stuff we've been talking about, but yeah. So this is an ellipse with eccentricity 0. It turns out to be this red ellipse right here. It turns out to be a circle. And then if we have the eccentricity 0.2, we have this green ellipse right here. And then the more the eccentricity, the more we get to something like this. So, so if we look at the actual orbits of the planets, it's an ellipse. It's not just going around the sun in circles. There's tiny differences throughout the year of the length between the Earth and the sun. Now, that doesn't mean it causes everything. There's other factors, such as the tilt of the Earth and so on. But yeah, pretty sure. Hope this is cool. And also it's 2:07, so if you want to go now, you can go. But now I'll go on to something different. So now we have. So now we've been dealing with these equations with x squared and y squared. But what about an equation that instead of so we can keep this x squared, but what if we turn back a notch on the y squared and just say y? So y equals x squared. What does that look like? And some of you might have learned this. It looks like a smiley face, which is a parabola. Okay, so if x is 0, then y is 0. If x is 1, y is 1. If x is 2, y is 2 squared, which is 4. And then 3, 9. And then if x is -1, y is 1. -1 squared, which is 1. -2 squared is 4. And it's basically symmetric on both sides. So it looks something like this. A smiley face or a parabola. And so for the circle and the ellipse, we both had, for both of them, we had some sort of center. For the circle, it was easy. The center to any point had the same length, the radius. For an ellipse, well, there were two centers. And it turns out that if we had any point on the ellipse, then we would have to use both the distance to both its centers, which are these centers are actually called its foci. Okay, so if we call the two different lengths, A and B, A plus B is the constant. So the constant is not just one of these lengths, or else it would be something like a circle or something. But the constant is rather the sum of A and B. So if we had this point right here, A like C and D, then A plus B would equal C plus D, because they're the sum of the distances to the foci are the same. So we had some sort of center. So for the parabola, we might wonder, is there a similar center? Well, where would that center be if there is one? Would it be somewhere right here? That would be really strange because it's not really symmetric. It looks far, like some point right here would look pretty far away from the parabola. So it's probably somewhere symmetric, so somewhere along here. And if we had one right here, it would be kind of weird. So so it turns out the center is somewhere right here. And we can zoom in a little on the parabola. We can scale X and Y differently, so that we have something more like that. Okay, so we have some point right here as the center, but it's not really, there's like for this the circle. For the circle, we had everything symmetric around it, right? Because we had one center and everything was symmetric around it. For the ellipse, it wasn't everything was symmetric around one center. We had two foci. So it turns out for the parabola as well, we have two things that define it. And the other point turns out not to be a center, but a line. So it's not a point, but a line. The other center is something like this. It's a line called the directrix. So this is a focus. This is the focus of the parabola, and this is the directrix. Those vocabulary names are kind of, you can, I don't remember them. Like you can just forget them after the, you can just forget them after the lesson, the focus and the directrix. But for here, we're going to use those names. Okay, so this is the focus, this is the directrix. They're sort of centers in a sort of way. And so what does the property turn out to be? For ellipses, we had this weird property where the sum of the distances to the foci are the same. For here, it turns out that this distance and this distance are the same. Now, it doesn't look that way for this parabola, but if we choose the right focus and the right directrix, we get it. And obviously, since these two don't look the same, well, what choices for the focus and directrix do make them the same? That is a question that we can proceed with some sort of equation, right? So what is this distance right here? If we draw this right triangle, we can find it. So this distance right here is x. This distance right here, this whole distance is y, which is x squared. And then say the distance from this point to the focus is a. It turns out that the distance from this point of symmetry to the directrix is also a. So we can say that this length right here is x squared minus a. And this length right here is x squared plus a. So what we end up getting is that this length right here, which is the hypotenuse of a right triangle with legs x and x squared minus a. So that length right here would be the square root, by the Pythagorean theorem, would be the square root of x squared plus x squared minus a. All that squared. And then apparently that length right here, right there, is also equal to this length right here, to the directrix. So that would be x squared plus a. So these two are equal. Now, how do we find what a makes a good focus in directrix? Well, what we do is well, we have this weird square root here and then these squares inside. So what we can do is like square both sides to take away this annoying square root. So x squared plus a, that value squared, is equal to x squared plus x squared minus a squared. And now we see that we have this thing that involves a, this thing that's just x, and this thing that involves a again. So we can move all the things involving a to one side. So we have x squared, lonely x squared, equals x squared plus a squared minus x squared minus a, that value squared. And if you have heard of difference of squares, you can do this using difference of squares. So that would be the sum times the difference. So what if you don't know the difference of squares, you can also just multiply this out and or just square this and expand and then subtract. It's not that difficult either, but if we do the difference of squares, then the sum is x squared plus x squared minus a. The plus a and minus a cancel out, and we get 2x squared. And then for the difference, we have x squared plus a minus x squared minus a, and then the x squareds cancel out, and we have a or plus a minus a, and then minus a becomes plus a again. So plus a, which is 2a. So this, all in all, is 4a x squared. So we get 4a equals 1. So a is 1/4. It turns out for all parabolas, this distance from the focus to this symmetric point, not sure what it's called, is 1/4. So, or is 1/4 of the constant you put here. So the general equation, if we don't need this right now, the general equation would be something like 4ay equals x squared. And obviously you can do various transformations to x and y to make it shift to the right, shift to the left, or up and down, have different roots and stuff like that. But to see the focus in directrix, I think this is the general form that makes it most clear. And then for the parametric equation, well, the parametric equation here doesn't seem to give as much insight as the last ones, which involve cosine and sine. The parametric equation here actually is just you plug in something t for x, and you get something t squared for y. So you want to have, you know that this is a square, so this should also be a square. So 4 is also already a square, but it's the square of 2. So you have a 2 somewhere here. A is by itself here. So you want some a here so that you get this being a square as well. So what we do is put 2at for x, and then when we put x is 2at, you get x squared is 4a squared t squared. So then canceling the 4a's on both sides, we can get y is a t squared. So this is the parametric equation, and it's not as insightful as the ones with cosine and sine, but it's still something. So this is the this is the equation that tells you about this and this, the focus and directrix. Now, where do you see parabolas? Right, we can see parabolas in we see parabolas in a lot of different in various different things. So can anyone think of any yeah, we can, yeah, satellite dishes. Someone said satellite dishes. We can also see them in physics and trajectories. So like if we shoot a basketball, that gives us a parabola. If we can, there's a lot of different places where you can use parabolas, and here are just some of the examples according to the Wikipedia page. So the basketball example, parabolic trajectories of water, and so on. Someone said satellite dishes. We also have a solar cooker, so pretty efficient. Solar energy to really collect and focus the different energies and stuff like that. Microphones. So yeah, hopefully hopefully y'all got something out of this, and this and if you are interested in these things, these various shapes that you can get from equations, what these shapes are actually conic sections. So here's the Wikipedia page for conic sections. We had the circle, which we talked about, the ellipse, and then the parabola, and there's also one called the hyperbola. Okay, so here's the parabola, and then to get the circle, you basically cut across like this flat, and then to get the ellipse, you cut across sideways. And then to get this other shape, the hyperbola, which we didn't get today, you do something like this. And for next time, not next time, but at some point in the future, at some point in the future, Ben will actually be going over conics in more depth. So if you like these shapes, if you think they're interesting, the way that you can see them in different applications, then definitely go to his attend his lesson. So thank you all so much. And yeah, an oval is an ellipse. So thank you all so much, and have a great day. Great. Juneteenth yesterday, Father's Day tomorrow. Yeah, have a great day. Thank you so much.